Hey, hello once again. This video is going to be all about how to solve math problems using Newton's second law. As you're watching this video, make sure you hit pause often. Make sure you're working the problems along with me, just as if we were in class all by ourselves. Since this is a video and you have the ability to pause, as you're taking notes, you should also write down why certain steps are being taken. So don't just write down the problem, but give yourself a really good set of annotated notes. Okay, let's begin with our first example. Okay, you're given a free body diagram, and our goal is to find all of the forces that are missing. Okay, so let's kind of start looking at what we've got. We've got friction going to the left, an applied force to the right, a normal force acting upwards, and our force due to gravity acting downwards. Okay, let's think about the y direction first. Okay, if I look at all of the forces acting in the y direction, it's typically safe to say that they are in equilibrium, which means the sum of our forces are equal to 0. We've got our normal force acting upwards and our weight acting downwards. Putting in what we know the force due to gravity is 80 newtons, so the normal force must be 80 newtons acting upwards. Okay, I'm going to put that in then up here. Okay, so we have 80 newtons of force acting upwards. I want to find my net force as well. Okay, net force is the same thing as saying the sum of the forces. We've already done the sum of the forces in the y direction, so let's sum the forces in the x direction. Okay, notice how we have 50 newtons going to the right. That's from our applied force. And we have 10 newtons going to the left. That's due to the force of friction. Okay, summing those up or adding those together, notice how we're going to get a net force of 40 newtons. Okay, let's keep going. I also want to find mass and acceleration. We know to find acceleration, the sum of the forces is equal to mass times acceleration. That's Newton's second law. We have the sum of the forces. I'm missing both mass and acceleration. So let's think about what I can do to find mass. Hopefully you remember using our force due to gravity, we're going to find the mass of the object. Okay, remember, force due to gravity was just equal to mass times gravity. So we've got 80 newtons is equal to mass times 9.8 meters per second squared. Okay, notice how I'm not using the negative 9.8 meters per second because the direction is given to us in the free body diagram. So I don't need to include the negative number. Plus, it's not possible to have a negative mass. When you type that in your calculator and work it out, you're going to get a mass value of 8.16 kilograms. Okay, now that I have that information, I can solve for my acceleration. We've got 40 newtons as our net force, or the sum of the forces. We now have mass. The goal is to find how quickly this object is accelerating. Plugging into our calculator, we're getting 4.90 meters per second squared. Okay. Now I've got all of the missing information. Okay, let's look at another problem. Okay, here's an example of something that's being pulled across a surface. Notice the applied force is at an angle. We've got our force due to gravity acting down, our normal force acting upwards, and they're telling us that it's a frictionless surface. Okay, so based on this free body diagram, I want to figure out first the magnitude of all of the forces, how quickly that block is accelerating, and how fast it's going after 2 seconds. Okay, so let's start with finding the magnitude of all of the forces. Okay, remember with vectors, anytime I see a vector, I want to split it into components. So I'm going to start with that applied force right there. Okay, we've got 50 newtons acting at a 45-degree angle. I'm going to take that, exaggerate it a little bit just so I can draw my triangle. Okay, and basically I want to find the x and y components. I'm going to find the y first. I'm going to take the hypotenuse times sine of our angle. Working that out, I'm going to get 35.35 newtons. Okay, since this is a 45-degree triangle, my x direction is the same thing. Okay, so my x component is going to be 35 newtons. My y component is also going to be 35 newtons. I'm covering up that 50 applied newtons on purpose because once we break it into components, we no longer need the hypotenuse. Okay, I've got the magnitude of each component for my applied force. Let's find our force due to gravity. Okay, we know that to find that, we're just going to take mass times our acceleration due to gravity. Okay, or 20 kilograms times 9.8 meters per second squared. When I solve for that, what I'm going to get is 196 newtons. Okay, I've got one more force I need to find, and that's the normal force. Remember, the definition of a normal force is just a support force acting on the surface. Okay, since it's acting in the y direction, I'm going to sum the forces in the y direction. So I've got everything acting upwards. I've got my normal force. I've got the y component of the applied force, and I've got my force due to gravity acting downwards. Okay, this is my equation for trying to find the normal force, and I'm generating it from my free body diagram. Okay, it's pretty safe to assume that this isn't going to accelerate through the ground, so when I sum those forces together, I'm going to get a 0. Putting in what we know is going to allow me to solve for that normal force. Working out my algebra, the normal force comes out to be 160 newtons. Okay, one thing I want you to notice with this problem is that the normal force and the force due to gravity are not equal to each other. The ground does not have to push up with as much force as if there was no other forces acting in the y direction. But because of this guy right here, the ground doesn't have to push up with as much force anymore. Okay, so far what I've got the components in each direction, I've got my force due to gravity, and I've got my normal force. I've found the magnitude of all of the forces acting on the object. Okay, let's find the acceleration of the box next. To find the acceleration of the box, what I'm going to use again is Newton's second law. The sum of the forces is equal to mass times acceleration. I've already determined that the sum of the forces in the y direction is equal to 0. I'm done with that. Now what I care about is all of the forces acting in the x direction. If we look at what's acting left to right, the only thing we've got is that 35 newtons, which is the x component of the applied force. So I'm going to put that in for the sum of my forces. I know mass. Now I need to find acceleration. Once I get to this step, it's just a real simple algebra problem. Okay, and I'm going to get 1.77 meters per second squared. Okay, found the magnitude of all my forces, found the acceleration. Now let's look at the velocity, or how fast it's going after it's been moving for 2 seconds. Okay, let's set up our guess method. We know acceleration, we just found that. We know our initial velocity is 0. The goal is to find the final velocity, and we're also given time of 2 seconds. Looking at those variables, we know we have an equation that says the velocity at any point in time is the initial velocity plus the acceleration times time. Initial velocity is 0, so to find that velocity after being pulled for 2 seconds, I'm simply taking my acceleration times how long it's being pulled. Okay, so I'm getting a value of 3.54 meters per second. Okay, so to summarize some of the things you have to think about when solving Newton's second law, okay, you always start with a free body diagram. No matter what, okay, draw your free body diagram. The free body diagram lets you know what forces are acting on the object, and it leads you to determining what the sum of your forces in either the x direction are or what the sum of the forces in the y direction are. If we're in equilibrium, both of those values are going to equal 0. We can be in equilibrium in one direction, not the other, or we can be in equilibrium with both. If we're not in equilibrium, then the sum of our forces is equal to mass times acceleration. So when you set up your problems, you're always going to sum your forces based on your free body diagram and then determine, is it in static equilibrium? If it's in static equilibrium, set it equal to 0. If it's in motion, set it equal to mass times acceleration. Okay, if you need to review anything, watch the parts of this video over again. When you feel comfortable doing Newton's second law problems, try the worksheet. The worksheet is a little bit harder, only in that you have to draw your free body diagram first. But you guys should all be pros at that by now. Good luck!